This video is on solid revolution. I have this yellow region right here, and I'm going to revolve it about the y-axis and then find the solid revolution. So this is the yellow region right here, and we're going to revolve it about the y-axis, and the this line right here, this is the line y equal to x plus 2, and then the curve here, this is the graph of y equal to 0.2x squared plus 2. And so let's revolve it about the y-axis. And so when we revolve it about the y-axis, then we get an inner solid revolution, and then we also get an outer solid revolution. And so this is what the outer solid revolution looks like, and then this is the inner solid revolution looks like. And here's both of them. And so to find the volume of the solid between the inner and the outer solid revolution, then what we can do is find the volume of this inner solid revolution and then find the volume of this outer solid revolution and then subtract. And so let's find the volume of the outer solid revolution first, and just like before, to find the volume of this solid revolution, we would divide it into many thin slices, and then find the volume of each slice, and then add the volumes of the slices together, and that will give us an approximation for the volume of this solid revolution. And so here's what a typical slice would look like. So this is the ith, let's call it the ith slice. So let's go find the volume of this ith slice. And so the first thing we need to do is find the points of intersection right here. So this line right here is the line y equal to x plus 2, and then this curve right here, this is the curve y equal to 0.2x squared plus 2. So we need this point right here, and we also need this point right here. So to find the points of intersection, we would just set the two equations here equal to each other. So we set 0.2x squared plus 2 equal to x plus 2. And then subtract 2 from both sides, and then move the x here to the left side, and we'll get 0.2x squared minus x equal to 0. Common factor is x, so we get x times 0.2x minus 1 equal to 0. Set x equal to 0, and then set 0.2x minus 1 equal to 0. And then solve this equation right here for x, which is 5. And so when x is 0, y is 2, and then when x is 5, y is 7. So the points of intersection, this point here is 5, 7, and this point here is 0, 2. And then also, since the axis of revolution is the y-axis, then we need to go ahead and solve these equations right here for x. And so y equal to 0.2x squared plus 2. And so move the 2 here to the left side, then we get 0.2x squared is equal to y minus 2. Divide both sides by 0.2. Take the square root of both sides, we get x equal to the square root of y minus 2 over 0.2. Since this curve right here is on the right side, so it'd be the positive, because when we take the square root, technically it's supposed to be plus minus here, so this is the plus, this is the minus, but we only need the plus part. So now x is a function of y, so let's rewrite this as the f of y equal to the square root of y minus 2 over 0.2. And then we'll do the same thing for the equation y equal to x plus 2. Then we get x is equal to y minus 2. And let's call it the function g of y, which is minus y equal to y minus 2. So this curve is f of y equal to the square root of y minus 2 over 0.2. And this straight line right here is g of y equal to y minus 2. So we have just seen that this point right here, this is 0, 2, and this is 5, 7. And so the first thing I'm going to do is I'm going to divide the interval from 2 to 7. So this is 2 up to 7 into n number of sub-intervals. So here's 2 and then here's 7. And then let's call the first value, let's call it y sub 0, and then y sub 1, y sub 2, y sub 3, y sub 4, and then eventually we get to the ith sub-interval. So this would be y sub I minus 1, y sub I, and then we'll get to y sub n, which is 7. And so let's say that we want 5 sub-intervals, and then the length of each sub-interval would be 1, because we would get 7 minus 2 over 5, which is 1. And so the thickness of this ith disk would be 1. If we divide the interval from 2 to 7 into 50 sub-intervals, then the length of each sub-interval would be 5 over 50, which is 0.1. And then the thickness of this ith disk is 0.1. And so in general, the thickness of the ith slice is 5 over n. And so let's denote it as delta y. And now let's find the volume of this outer solid of revolution. And so once again, to find the volume of the solid of revolution, we would divide this solid of revolution into many slices. And this is one of the slices. And so let's then call this the ith slice. And it comes from this interval right here. And so this would be y sub I minus 1, and this right here would be y sub I. The distance from the y-axis out to the graph right here would be f of y sub I. But f of y is the square root of y minus 2 over 0.2. And so f of y sub I would be the square root of y sub I minus 2 dividing by 0.2. But also notice that f of y sub I in this case is also the radius of the ith disk. So the radius of the ith disk is the square root of y sub I minus 2 over 0.2. And so the volume of the ith disk is pi times the radius squared times the height. But the radius is the square root of y sub I minus 2 over 0.2. And then the height of this disk is just the thickness of the disk, which we denoted as delta y. So the square root of this expression right here inside squared, it just y sub I minus 2 over 0.2. So the volume of the ith disk is this expression right here. And then now if we divide in the solid here into n number of slices, then the volumes of n slices or n disks would look like this. This would be volume of slice number 1, slice number 2, and then the nth slice. Using summation notation, then we have I running from 1 to n with the expression pi times the square root of y sub I minus 2 over 0.2. And then times delta y. So once again, delta y is the thickness of the ith disk. And then this expression right here, this is the radius of the ith disk. And then this expression squared, then we get y sub I minus 2 over 0.2. And therefore this sum right here is the volumes of n slices or n disks. And so the volume of the solid of revolution, of this solid of revolution, would be approximately this sum right here. And if we want the exact volume of the solid of revolution, then we have to divide the solid into an infinite number of slices, meaning allowing n to run to infinity. Then we would write it like this. It'd be the limit of this sum right here as n approaching infinity. And then when this limit right here, this limit quantity, when it exists, then we would define it as the interval from 2 to 7. Once again, 2 to 7, this is 2 to 7. Y minus 2 over 0.2, and then we can rewrite, and then dy, and then we can rewrite this as pi over 0.2, and then minus y minus 2. And then the integral for y is just y squared over 2, and the integral for 2 is just 2y. And evaluating from 2 to 7, so when y is 7, we get 49 over 2, and then we get 14. And then when y is 2, we get 2, and then we get 4. And then simplify everything, it'd be 125 over 2 times pi. And therefore the volume of this outer solid of revolution is 125 over 2 times pi. And now let's find the volume of the inner solid of revolution. And so here's the inner solid of revolution, and just like before, to find the volume, we would divide the solid of revolution here into many slices, and this is one of the slices, and so this is let's call this the ith slice, and it comes from this interval right here. So right here it would be y sub I minus 1, and right here the height would be y sub I. And so the distance from the right here, this is y sub I, and so the distance from the y-axis out to the graph of y equal to x plus 2, or the graph g of y equal to y minus 2. The distance from here to here would be g of y sub I. So this distance is g of y sub I. But g of y sub I here is also the radius of this ith disk. And so the radius of the ith disk for this inner solid of revolution is g of y sub I. But g of y is y minus 2. And so g of y sub I is y sub I minus 2. And so the volume of the ith of this ith disk would be pi times the square of the radius times the height. The radius of this ith disk is y sub I minus 2. The height of this ith disk is just the thickness of this disk, which we denoted as delta y. So this is the volume of this ith disk. And if we divide this solid of revolution into n slices, then the volumes of the n slices will look like this. This is volume of slice number 1, volume of slice number 2, and volume of the nth slice. Using summation notation, then we have I running from 1 to n, with the expression pi times y sub I minus 2 squared times delta y. And so once again, delta y is the thickness of the ith disk. The radius of the ith disk is y sub I minus 2. And then simplify this expression, the expression y sub I minus 2 squared. We get y sub I squared minus 4y sub I plus 4. So the volumes of n slices is this sum right here. So the volume of the inner solid of revolution will be approximately this sum right here. And just like before, if we want the exact volume for the solid of revolution, then we need to divide the solid of revolution into an infinite number of slices, meaning allow n to run to infinity. And then we would get an expression like this. The limit of this sum right here is n approaching infinity. And if this limit quantity right here exists, then we would define it as the integral from 2 to 7, because it's 2 to 7. And then we get pi, and then y squared minus 4y plus 4, and then here we get dy. And then integral for y squared is just y to the third over 3, and then the integral for 4y is 2y squared, and the integral for 4 is just 4y. Evaluating from 2 to 7, if we plugged in 7 here for the y, then we get 133 over 3. And then when we plugged in 2 for y, replace y with 2, then we get 8/3. And then simplify everything, we get 125 over 3 times pi. So the volume of the inner solid of revolution would be 125 over 3 times pi. And so the volume of the solid of revolution that we're looking for is the one that is between the inner and the outer solids. And so the volume of the solid of revolution in between the two solids would be 125 over 2 times pi. This is the volume of the outer solid minus the volume of the inner solid. So we get 125 over 6 times pi. And that's the end of the video.